I was strategically choosing number 2, but now I realize following an act like that is very, very hard. So perfect. So I'm going to talk about managing service systems with dependents. And before I get into the topic, I thought I will say a few words about the operations department itself and what we do, and specifically what is the point of view that we have about operations. And when we think about operations, it's basically thinking about starting from the ideas, but getting into and thinking about execution. And here I want to start with a simple example, but a fun example, which is an example from a series called South Park. So some of you know about it. It's basically a series of 6 or actually 5 foul-mouthed kids, which we have a very good example in the core class. And in this particular episodes, they actually are trying to set up a business plan that they want to talk about. And since they don't have exposure to business, they go and look for a character which looks like this. And this character named Gnomes, there are a bunch of these, they go out and collect underpants. So they follow them, they catch them, and then they follow one day, and they find a full pile of underpants. And they say that, what's your business? Like, what's your business plan? They say, this is just phase 1. We're just collecting underpants. That's what they say. Say, what's phase 2? So everyone looks around and say, what's phase 2? And then they go to a board, and they say, that's our business plan. Phase 1, collect underpants. Phase 2, phase 3, profit. And that's exactly, if you take a moment and think about, that's what we hear a lot. Many times people come up with brilliant ideas, say there is a big market, we're going to do this. And that's where ops basically sits, that you have to think about how to take the idea, think about your strategic position, but turn into execution. So that's what our point of view is, and that's what we basically think about, right? So if we look at, there are lots of great ideas, strategy, defined vision, what you want to do, which was also lacking, by the way, when we looked at the South Park example. And obviously, we want to get to these outcomes. And the question is, what is in the middle? And that's where we want to think about the operations, and that's what we will be looking at, right? The reason I want to make sure that we do this is so that you understand where the motivation of what we will be looking comes from. That we want to, while we want to make sure that that execution is done well, we want to think about what the customer wants, how will they behave. That will start coming together. So here is the definition of operations, which is it's the management of business processes, and the key phrase there is recurring activities. And specifically, if you think about the word operations, it comes from the opus word work. And interestingly, it has a more contemporary meaning, which is an artistic work. So if we take a moment and put both together, we want to think about operations is science and art of making repetitive work, which is very essential, as I pointed out, better. That's what we want to do, right? And just to show the same thing one last time, when we're thinking about a business plan, many people start with, we want to deliver great service, consistency at scale. But underneath that statement, there are lots and thousands of operations decisions about how do you manage your queue, how do you manage your service, how much staffing do you need? All these will be the operations question that we want to answer. And given that it's a technical talk, I have to use these words, necessary and sufficient. This is going to show up in theorems in a moment. So if you think about success of execution is necessary for the success of business, and failure in executing would be sufficient for the failure of business. And that's why we have to really take a closer look and think about operations and try to understand how we will do the execution. Now, within that, if I look at ops, it talks about work that is being done. And specifically, when I look at today's talk, we will be focusing on services. So then comes a natural question, why we look at services. So services actually represents a big part of the modern economics. Specifically, if I look at GDP, it's around 80% of the US GDP in terms of employment, growth. And there are all these different areas like healthcare, finance, retail, platforms, education, logistics. We ourselves, what we do, is a big part of services, and that's why it's worth studying and trying to understand how to manage them well. Now, how is services different than other operations? Because services has customer experience. There is a co-creation between customer coming and you delivering the product. And here the product is not just a physical good, it could be a soft, intangible good that is being delivered. There is a co-creation that happens, which is produced in real time, and we need to think about how does that interaction look like, and that's where it sits on the interaction of how you structure your process and how you think about the behavior. And what we want to do is we want to look at what has been done in this literature before the series of work that I will be pointing to, and why does that behavior become suddenly even more important as we try to structure this together. So the way we model services is, so think about, you can take a canonical example of a call center or think about a hospital setting, and imagine that there is a series of people coming. So this is a dynamical system. That's why these are harder to analyze. And the way we typically think about this as follows. A customer arrives, and they come with their arrival. They bring a clock, which is their service time. So they will wait in the queue until they get into the service, and once they are with a doctor or with the agent, they will start this clock. When the clock expires, their service is done, and then they would leave the system. But interestingly enough, if you have ever gone to emergency room or have called a call center, you know that we as customers don't like to wait. And all the apologies that the firm pushes on us just makes it even worse. And of course, some of the firms have the audacity while you're waiting to try to sell you things. Right? Means when you call Comcast, they say, my internet is down, I'm calling Comcast. They say, you can also get a phone line if you want. And I'm like, hell no. Right? And the other thing they try to do is they tell me that not only that, you can actually go online and actually connect with us. And I'm like, that's exactly the problem. So what you want to do is we want to think about this aspect, which is the abandonment that happens, which is a customer gets into the queue with the intention of getting to an agent, but as they wait in the system, they do not want to continue the service and abandon the system. So a very simple way to do that, just in the spirit as we have done before, what we can do is we can actually give the customer another clock that they bring with them, which is called the patience clock, or impatience, depending on how you want to call it. And as soon as they join the system, they start that clock. And when that clock expires, they will basically leave the system. And what we want to do is we want to take a deeper dive into this patience clock, because it's so important. Because notice, this is not just about revenue, but this also impacts, because you're making the system more crowded. Not only that, you are also having people who will finally not be served, so they will not generate revenue for you, and there'll be dissatisfaction. So you want to think about how do you manage these systems better. Okay? If I look at the traditional common assumption, as I mentioned previously, these systems are dynamical systems, so having just even everything independent makes it highly intractable to model. So people rely on approximations, but within that, there is a very crucial approximation that is being made, is that the primitive processes, which means your interarrival times, your service times, and your patience clock are all independent, and that is a very fundamental assumption that has been used throughout the literature. And that gives you some tractability to work with. However, if I look at the literature, it actually points out that that is not true. And a very simple test that people have done, and this is, interestingly enough, this has been done in a variety of settings. What people have shown is, in the research, that as the customer waits, this service time distribution does not look the same. So the people who have waited for 5 minutes versus the people who have waited for 10 minutes, their service times, the time that they engage with the agent, looks very different, which means that the independence assumption that we made previously to understand and come up with how to manage these systems is not true. And this is true in hospitals. This is true in restaurants. This is true at health outcomes. Sorry, just one second. And just to show you the feature behind that, like why this could be happening, for instance, if you think about health outcomes, if you do not get to the doctor as quickly as possible, your health can deteriorate, which means that there will be more effort needed to get or stabilize you. Chan et al. See this in ICUs. At restaurants, if you make you wait more and you have a limited amount of time, you will try to finish your food sooner. People have also shown that people also feel more privileged. One of the very famous examples that people have shown is that if you look at ice cream parlor, if you stand for a long time when it's your turn to get ice cream, you feel that you have earned the right to taste more flavors. Why not, right? Because you see other people have caused that externality on you, so you feel that, okay, I'm not going to see, it's my turn now, and I'm going to make sure I do not make the wrong decision. In call centers, I can clearly see this. The more I wait, the more upset I get. So many times when I get to the call center agent, I ask them that this was just a pretty bad service. And the person said, but that was Comcast. And I said, for me, you are Comcast. Right? Because that's the only touch point I have. So I have to give my input to them. And that's where you can clearly see that extra time that you cause leads to your services being different duration. And that dependency is what we want to actually think about and look at how we can model it. Okay? Now, if I start looking at the modeling of this idea that, remember, we only have data that we collect, which means that we know when the customer arrived to the system, we know whether they waited enough to get into service or they abandoned the system. The question is, from the data, can we think about why would this observation that depending on how long you waited, your service looked different? And there could be two things that could be happening. Idea number one, that there could be exogenously bringing this dependence from outside the system. So we are not doing anything. This is simply happening the way they arrived, the two clocks that they brought with themselves, one for the service time and one for the patient's time, are not independent, but they are correlated. Just to give you an example of this, imagine you going and wanting to buy a loaf of bread or just one ingredient that is missing in the dish that you're making. You will be pretty impatient because you want to quickly get into the store, buy that ingredient, and leave the store. So you went to the store with thinking about how long will you stand in the queue, and if you see it's busy, you will just go to the grocery store next door to get that particular ingredient. So the wait time did not influence your service time, but your patient's time and your service time were related, and there is selection that is happening which changed the services I will see based on how long you wait. Right? In contrast, it could be endogenously created due to the variability in the wait. If I make you wait more, you will turn around and hurt the system more. This was basically the example of the ice cream tasting example that I mentioned, that you waited a long time. So now what you do is, when your time comes, you are going to take a longer service time. We refer to this as endogenously created dependence and exogenously created dependence, because in one case, you bring that dependence from outside, and in the other one, you have created that dependence as you interact with the system. Interestingly enough, both of these have been somewhat discussed, like some of my earlier work. And the question that we were curious about is that, A, do these dependencies matter? And second, from the data, can we disentangle which dependence is there? And this is where you can clearly see that as I want to design these systems and come up with staffing policies, think about what will be a way to run these systems, it will be important to understand whether the customers are coming with that, that's on the left-hand side, or my making them wait actually influence that, and that is why they are behaving in a certain manner. Right? Okay. So for that, first things first, we would want to establish that these dependencies actually have a non-trivial impact on the running of the system. Because if this dependence causes a few changes, remember these are stochastic systems, there is anyway variability, this variability would not be significant, then it is not worthwhile even studying. Because if you're managing, you want to know that will this relationship have an impact or not. So here is a simple simulation example to convince that this dependence matters. And in this particular case, I have taken the dependence of the exogenous case, which is they came with two clocks. And you might say, what about the other one? You will see in a moment that once I show you this one, that will become the relevant one, and we'll discuss that. So what is the setup? The setup is as follows. As we look at two-dimensional distributions, they will have what we call marginals, which means if I ignore the other dimension and just focus on how one dimension is distributed, so I'm choosing a system where the marginals have been fixed. So if I look at just the distribution of services, just the distribution of patients, that's exactly the same. And what I do is I vary the distribution or the correlation, the joint distribution, by changing the correlation. Now, interestingly enough, we all know this fact that correlation is equal to 0 does not mean independence. Independence means the correlation is 0. So correlation by itself does not tell me how we will generate the two random variables. So there is another freedom that I have. But without getting into those, here is how the graph looks like. And there is multiple points with correlation 0 because that blue dot there specifically is the independent version. But I can create correlation of 0 with other distributions. And what we find is that there is a non-trivial impact of dependence on the queue length. And you can clearly see that it can be as large as from going from 22 to all the way, if the correlation was perfectly correlated, just to show you the range, it gets close to around 85. So what this tells us is the dependence has a non-trivial impact. It is worth studying because if we do not account for it, our metrics will be extremely incorrect because we have omitted something as important as dependence. Now, what are the issues with the estimation? The couple of issues. Number one, we have to understand what kind of dependence it is. Number two, distributional fitting itself is hard. When you're doing two-dimensional distributions, it's hard to fit those. Not only that, when I think about service systems, there is another level of complexity that comes in, which is censoring. So notice the people who abandoned, I absolutely perfectly know their abandonment time, so I know the clock that they were carrying based on which they abandoned. But for those people, I have no clue what their service clock was. In contrast, the people who got into service, their abandonment clock is not visible. The only thing I know about them is that the abandonment clock was long enough that they've stayed in the queue until they got into service. So there is censoring on either side. We never have perfect information. And this is an issue with how would we take the data and convert it into these models. But this issue that I just mentioned, the censoring issue, will actually lead into something very, very interesting, and that's what we want to get to. Everyone comfortable with the censoring, right? Means you cannot observe both your patient's time and service time. So whichever model, whichever way I cut it, you will only have censored information. Okay. So here is the model setup, and here just to the reason for showing symbols is to convince you that I'm not doing funny business. This is all rigorous. So what we do is we take the exogenous model. Remember, this is the model where people come with two clocks with them, and I'm going to just take those clocks and denote them by S and T. And S and T together will have a joint distribution. In the endogenous system, what they come up with is they come up with a clock, which will be their patient's clock. And they have another clock, which is Si of Z, which is their service time clock. So I tell them how long I will make them wait. And then they will open the book on that particular page and pick the distribution. Because I made you wait a particular time, you will use that distribution for your service. Now, just to remember, this is just a modeling. Remember, people are not actually doing this, but their behavior can be modeled by this. Now, to make sense of it and to give a particular statement that will become important, I'm going to use this terminology of probability law. That's what we use in the paper. But the way you want to think about it is, if I give you the arrival pattern and the number of agents, how is the dynamics of the system behaving? That's what we call by the probability law. So this is the probability law for the system dynamics. So you can imagine that there is some probabilistic rule along which the evolution will happen given some arrival and some number of agents. Now, we will say, and this is the terminology that we will use, that we will say that an exogenous dependent system and the endogenous dependent systems are equivalent if this law is exactly the same. And what do I mean by that? If I look at the evolution of this queue, that will not change either it was exogenous or endogenous. If they're called equivalent, they're basically behaving the same way, right? And with the definition now, we can actually think about our result. So the first thing is, these are the two models, and we want to understand their relationship. So I'm going to do them with simply Venn diagrams. Now, it's very clear to us that there should be models where it can have an exogenous representation as well as an endogenous representation. And it's very trivial. Take the independence case. If things were independent, we could have called it exogenous or we could have called it endogenous. So these two models are not completely non-overlapping. So there are at least something in the middle. Now, interestingly enough, we can actually show that the relationship is actually more nuanced than that. For every exogenous model, we have an endogenous model, but not the other way around. And the reason for that is exactly the censoring that I mentioned. Because of the censoring, for every exogenous model, I can write down an equivalent definition which will look like the endogenous model. So what this is telling us is, if I collect data, and it happens to have some monotonicity property, which we'll talk about in a moment, you can write it as an exogenous or endogenous, and you will never be able to figure out what kind of dependence they have. In contrast, there could be data which falls in this side, which will be purely endogenous, but I cannot separate out and say with certainty that there is exogenous dependence. That's just not possible. And this is what that formally looks like. And the way the proof is done, I would not get into the details of the proof. The proof essentially is a coupling argument, which is used in probability, where you take one system and show that if I have the clock for everyone according to those laws, I can create clocks in the other system that will look the same. And as I mentioned, the key part of that proof is exactly that, what I've highlighted in blue, in the red part, which has to do with the fact that there was censoring, and that gives me enough flexibility to actually make that happen. So remember that censoring, which was an issue, was exactly the reason why we can actually construct this equivalence. Now, if you take a moment and think about it, I said this dichotomy of the two models. One was endogenous model, where my weight cost you to change your service time. And the other model where we said that you came with a two-dimensional distribution. But one can actually think about even a more general model. What is that more general model? That more general model is that the service time depends on both their patient's time as well as the wait time their system. So as you wait, and the two clocks are actually are related, so your patient's time that you drew, which you came with, and the service that you're drawing based on your wait are actually related to each other. Now, if you take a moment and think about it, it might seem like, oops, I already gave the punchline away, sorry. So you might feel like that this is how the structure looks like, that we have a more general model. But we can also show that this generality is just a complication. You don't need that generality. What you have is that the exogenous model is subset of the endogenous as before, but the general dependence that I'm just talking about is not more general than the endogenous model. So that is the most general model that one can think about. Now, obviously, the next thing that comes up is that can we go the other way around? And the answer is no, sorry. Only if there is a monotonicity condition, which I've written right here, that if that particular function is monotone, then only you will have an endogenous dependence given the exogenous model, but not in general. So this is basically the converse of the model relationship that we have. So what have we seen so far? So let's just take this talk at this point. We saw that for every exogenous model, there is an equivalent unique endogenous model, and the general dependence is not any more general than the endogenous. So we can only distinguish between these two models partially if we want to understand the mechanism. And we only have collected the data based on how much time they spend waiting and how much time they spend in service. Now, of course, if you go and ask them upfront, unless you do that, then you cannot disentangle. You can obviously create experiments and other things. That is where you might be able to get a little bit more headway between the two models. Okay. Now, the next question that is important is that why are we doing this? So remember, we are talking about two models, so it will be worth thinking about what is the reason between choosing or asking the question about the exogenous and endogenous model, and that has to do with the system dynamics. Interestingly enough, the smaller one, where the customer comes with this bivariate distribution, one can show that those models are actually somewhat nicer. The steady state is achieved, and not only that, it's a unique point, and you can show that what it will look like. In contrast, that bigger model that I showed you, which is the endogenous model, where our waiting caused people to change their service time, we actually see a much more nuanced way the system operates. So just this is showing you how the number of people in the system would look like if I run a simulation. And if I run it, this is what that distribution would look like. And the key point to note here is that while in the system on the left-hand side, you can clearly see that, let me try something. Nice, right? So in this particular case, you can see that all of them are centered around 100. That's where it is. In contrast, in this particular system, what you observe is that the queue sometimes stays around 150 and then comes down to 100, spends sometimes there. So there is some sort of a phase transition that is happening, which means that there is more uncertainty, there is more atypical behavior that we observe when there is endogenous model. And the question is, why is that happening? Can we say something more meaningful about the systems with the endogenous dependence? Okay. Now, how do we approach that question? That question also has one more observation that I want to bring up. Depending on where you start, which is essentially that these two, which I just showed you, you might say, OK, but that doesn't matter. That was still close enough. But depending on where you start, you might have a very different phenomena, which is what we're observing. In this case, I've taken the same system, same everything, except I started one empty, and that's why it stayed around 100. And in the other one, it was non-empty. I started from a high level. It never came back. Even though you have enough capacity, and we call it the state, means this is basically what's happening is you have a long queue, and everyone who came to the server deserved more flavor of ice cream to be tasted, and that led to the queue having a bad outcome. So what we want to understand is why are these happening, and can we make sense of this? And the way we approach this is we want to understand that why are there multiple regions in steady state and what's going on. As I talked about, queuing systems are notorious for intractability, and even with dependent systems, we know very little in a closed form for these. And most of the time, we actually analyze them using some sort of an approximation or thinking about large system phenomena. And that's what we will do here. we will take what is called a fluid approach. And the way the fluid model works is as follows. It takes the stochastic processes that I defined, so the randomness in your services, randomness in your arrivals, but rather than treating them as random and uncertain, I will treat them as if fluid is flowing through the system. So every minute in time, I'm not thinking about the quantum of person showing up or not showing up, but rather every minute there is fluid coming in, there will be fluid which will be abandoning, and there will be fluid which will get into services. So there is a big literature on looking at the approximations in queues. There are fluid models, and as I mentioned, the dependent service and patience is a very nascent stream that we are looking at, but there is a big chunk of literature which does this approximation. And the way we want to think about it is, and I'll start with a very simple model so that we can think about that relationship. Imagine that the rate at which people are coming is denoted by lambda, and theta is the rate at which they will abandon, which will be multiplied by the number of people standing. If more people are standing, more people will be leaving the system because of abandonments. And I have n servers, each one of them has a service rate mu. Now, if you write down the simple balance equation, assuming that it's all fluid, you might feel like you have already omitted all the randomness, so will you be able to get something? And the answer is yes, and that's the beauty of these fluid models. If I take a moment and think about it, I simply do the conservation of flow. Whoever came in has to leave one way or the other. So either they will get served or they will abandon. That's the beauty of service systems. So what we get, the rate at which people are coming is lambda. That was the arrival rate. They will either leave through the services, which is n mu, or through the abandonment, which is theta q. So I have now a very simple approximation for the queue length. Of course, this was under the assumption that things were independent. And one can actually prove, there are pieces of literature on this, that this queue length that I just computed based on just the averages is extremely accurate to tell what is happening in the system. So average queue length is not, this is not just an approximation with a lot of error. This actually has an order 1 approximation. So as the system becomes large, the error that you're accumulating is not on a square root level, or as the system becomes large, it becomes more and more. In fact, it's a constant. That's what you're missing out. Okay. Now, the question is, how would this look like when we have dependencies, and not only dependencies, but it's not Markovian, which is that it's not constant rate. Depending on how much time you have spent in the queue will change what will happen. And the answer to that is in this particular picture that I will show you. So what we are doing here is just to explain the axis first. On the horizontal axis, what we are drawing is the amount of work that has waited in the queue for W amount of time. So as I go from left to right, I am plotting time, and the height here is the amount of work which is there, which has waited in the queue. So why is it dropping? So if you just look at the left hand, go to the left extreme, what we have, lambda is the rate at which people are coming in. Each one is bringing in 1 by mu amount of work. So if I look at just the amount that is waited for negligible amount of time, that is lambda divided by mu. As we are waiting in the system, we are seeing a decaying curve because there are abandonments, so the work is decreasing. And we will get to a particular point, which is W bar, which is where they will enter service. And just using the same rate in is equal to rate out equations, we can actually convert this analysis into an approximation for what the queue length would look like. And now we can ask the questions just like before. What is that queue length? And is there multiple equilibrium points? And how do these equilibrium points look like? So now we have set up the entire machinery that we can start rolling and start getting answers for our system. And this is what we have for the endogenous model. It's just basically the same idea for the exogenous and endogenous model, except both of them will have slightly different functions that will be driving it. That's the only change that will happen. Okay? So the question then becomes that, remember the W star that I showed you, because the work will decay and then it will get into service. The question is the W star unique? For the exogenous model, what we can show is that that number, that the amount of time people have to wait before they get into service, is unique. And the intuition behind that is driven by the fact that if you bring two distributions, remember the joint distribution that you're coming with, the service time and the patient's time, there is a unique W star. Because you're decaying your work, you will enter service. But in the endogenous model, where the wait causes you to update your service time, what would happen? If I make you wait for a long time, it might be that you have upped your service time so much that there is an equilibrium point at a higher W, or there is the equilibrium point at a smaller W. But we have now the equation to characterize those. And the way that works is we have this equation phi. If mu z is decreasing, there is a unique equilibrium. That's what happens with exogenous. But if mu z is not decreasing, and mu z is basically the rate of service if I make you wait for z amount of time, if it is not decreasing, which means that if I make you wait long time, you increase your service requirements, then you need not have a unique equilibrium. You will have multiple equilibria points. And that's exactly what we are picking up in these graphs. But the story is a little bit more nuanced, because let's imagine we estimate this. Is it true that we will be able to predict? And you can see that these are the two lines which I've just drawn. These are exactly the equilibrium point. And as I mentioned, if you look at the expected queue length, it exactly is spot on. That's what I meant by these are very high accuracy, because these are just with, I think if I'm not mistaken, 50 or 100 servers. So you don't need a lot of servers to make this happen. Now the next point is that, is it true that we have this defining equation which I have on the right-hand side, which is the lambda times the phi of z, which is the service requirement, needs to equal 1. If you find all the solutions to these, will all of them act as the equilibrium point? And the answer is no. Some of them might be unstable equilibrium points, and this is how the graph looks like. So that blue curve that I'm showing here is that phi of z, which is the conditional service time. And I'm drawing it at a line of 1. And you can see it's color-coded. There are 2 greens and 1 red. The 2 greens are the stable equilibrium point, and the red one is the unstable equilibrium point. And just to go back and draw this together, take a moment and think about it. If you're on the first green point, what you will find is if you move to the left, your services will be pushing you towards that point, and if you move to the right, it will push you up. That's why it happens. But if you are at the red point, if you move towards the left, if you're gone above it, it will push you away. So what is happening is once you leave it, you will try to go to either the left point or the right point. And this is exactly what we also see. So here is the same system, and the dotted blue lines are the 3 equilibrium points. And what we observe is if you start the system empty, you typically stay at one point. And if you start exactly around 215, which is the second one, you're still not budging a lot. But if you start above it, you start to get absorbed in the other one. So the middle one, in some sense, is not a stable point. It is pushing you towards the other side. And this now can get into how can we control these systems. Because what do we have? We, in some sense, have what we refer to as congestion collapse. Because my system was congested, people have updated their service time, which would lead to other people also waiting for a long time. So what this is suggestive is that when the queue length becomes very long, it makes a lot of sense to bring in more people just for a short span of time, or do something to dissipate that queue so that you can reset it. Not only that, we also try to do the following. We try to think about that we just need to bring it below 251 in this particular case, Because once you have brought it, why is 251? Remember, if you look at just the simulation result, just purely looking at Q, you would not even know that 251 is there, because it will nothing will look, there is nothing absorbing, there is not a state where things get absorbed. But interestingly enough, if you take your Q and you can bring it below 251, then suddenly it will get sucked into the Q length of 66. So it also is telling you that you do not need a lot of work to bring from the top, which is 348, all the way to 66. You just need to bring it enough so they can push the people into the smaller Q, the smaller Q length. That's what we can do, right? And this is simply showing you why it's happening. This is the unstable. And this has to do with the fact that if I look at the Q in this stage, it pushes you in this direction. In the upper one, it gets pushed in the opposite direction. And that's what we're able to prove. So just to think about all of this together. Sorry. So what the general result that we have in the paper is that in general, there are 2n minus 1. So there are odd numbers of equilibrium points. And half of them will be stable. And the other half, which will be the intermediate one, will be the unstable, which means that if you run the system on those, you would be pushed away, and you will want to think about the other. So what we are doing in terms of the follow-up work on this, so there is this PhD student who is looking at this particular problem. And what we've come up with is we've come up with policies. And one of the policies, which we love calling it the slingshot principle, just like when people launch satellites or they spend spacecraft, they use the gravity and turn it around. In a similar manner, what we are trying to do is we are saying that, remember, there are these force fields there, and you know where the boundaries are from the data now, because you will be able to figure out. Now you can that particular point, you just need to get your Q length in that neighborhood, and from that point on, it will automatically get sucked into the relevant Q length. So to conclude, just one sec. Here are the key learnings that we discussed. First, we talked about the dependent structure, looking at the endogenous versus the exogenous cues in terms of the dependence. Exogenous is when people come from the outside with the dependence. Endogenous is when our waiting time actually makes them change their service requirements. We saw that there is a relationship between them. These are not completely different, but actually, interestingly enough, the exogenous one is a special case of the endogenous, and endogenous one is much more general. Exogenous dependence is much nicer because there is a unique dependence. It gives you more stability in terms of you know exactly what will happen with the system. Endogenous suffers from this multiple stable equilibria, which needs to be handled more carefully. We also saw that if I think about even more general class of dependence, but still keeping them within the service time and patient's time, endogenous representation is the most general you can get. There is not another class that we are missing. And finally, there is this atypical phenomena. While exogenous is unique, endogenous is not. And as I mentioned, one has to think about how to control it and set it up properly. Thank you so much.
So I'm going to turn it right over for questions, and we'll have until 10:45.
Awesome. Thank you.
Okay. Well, very interesting. I saw a lot of IID assumptions sprinkled, so that bivariate system is kind of, does that mean that you pool all observations across a day or something like that? Because to me, a first order concern in these type of systems would be that my waiting time and my ability to wait and what I expect is in terms of the service time would differ depending on whether it's morning, noon, evening. If I call in the middle of the night, it's probably because I desperately need the service and I'm going to be very patient. In the morning, I might wait for the coffee for a little while, but I got to get to work. So if it takes too long, I'm going to abandon it. If I get up there, opposite of what you said, in that case, I would just want my coffee. I don't want to taste around because I need to get out of there. So the intraday patterns would influence the whole joint distribution in complicated ways, and I thought you would have to estimate it conditional of the time of day or what type of service it is.
Sure.
So how do you deal with that in terms of, I can understand the IID assumption is important, but there's got to be something else as well.
Absolutely. So what is good about queuing systems, while they are harder to analyze, Torben, what is good thing about them is the service times and the inter-arrival times. If you think about the time between one customer and the next customer showing up, and the amount it takes me to make coffee for you, is on a different time scale compared to the time scale on which the people's arrival behavior or their behavior changes. So notice that there is a morning traffic, but I'm making coffees every minute. In 30 seconds, I'm able to serve coffee. And the inter-arrival time is of the order of 90 seconds, 2 minutes. Whereas that behavior change will happen maybe in 3 hours. So the good thing is that within a few minutes, the system stabilizes to their equilibrium point. And this is how the call center staffing or many of the staffing works. They basically take the entire day, chop them into buckets, and then they will say that within these buckets, the IID assumption is true, and let's look at what is the steady state behavior there. And that's how it's done. Yeah. You localize it, exactly. And as long as that behavior is not changing dramatically in a very short span of time, one can prove that these are actually fundamentally the right way to do it. Perfect, thank you.